All right, so this session is rational inequalities. And if you watched my polynomial inequalities video, then you're going to find that this is very, very similar. And hopefully that will help you make the connections of what you need to do. And you'll see, oh, it's not so bad. You know, it's just a couple extra steps. Because usually, for one, the word rational freaks people out because that means fractions. And then we've got inequalities. So this just generally is like people read this and they're like, oh my goodness, it's not that bad. It's like the polynomial, which we found were not that bad. So I've actually designed this so it's going to be like following the same sort of pattern as the polynomial inequalities. The definition is basically exactly the same. The only difference is instead of a polynomial, we have a rational expression, we have a fraction. So the definition is the same. The less than 0, the greater than 0, those are all looking for the same exact things that we had with the polynomials. We're looking at whether our graph is above or below the x-axis, basically. So it's just a matter that the equation is different, but the steps are near identical. Just absolutely, just so close. So I'm not going to go into too much detail there. It's just reference. So I figured it's best to demonstrate with an actual rational inequality or rational expression here, a rational function. And because I'm actually, so they have their asymptotes in the same color as the, let's not use yellow. No, I don't want to use blue. Let's do green. The asymptotes are in the same color as the x-axis, so I'm going to just color them so you don't get it confused with where the x-axis is, because the x-axis is actually up there. So I'm going to color the asymptotes as green so you don't get confused. So we have this graph. This is a rational function, and we're determining the intervals. We've got 4 different possibilities here. So we're looking at the intervals that are less than 0, less than or equal to, greater than, or greater than or equal to. So the less than 0 part means it's below the x-axis. So I'm going to just use my highlighter to graph the parts where it's under the x-axis. And we're going to translate those to the parts of the x-axis here. So I'm just kind of, instead of drawing them, I'm just kind of flattening out so you can see what parts of the x-axis are graphed. Now with the asymptotes, you're just going to get close to there. So if you were to actually try to turn this into like an inequality, that you're going to have parentheses at asymptotes because you can't actually touch those. So if I use red to kind of graph this, we do cross here. Oh, but it's a less than. Less than means you can't touch it, so we can't include 0. So I'm going to have another parenthesis right there. And then where a graph is below the axis on these sections that I have highlighted and that I've drawn in red. So we've got 2 sections where our graph is below the x-axis. And because they're 2 separate sections and there's a gap in between them, we have to use a union to write it. So we go from left to right. So from the left, we have negative infinity because it goes on forever. And then it's at -2 where it starts crossing the x-axis and starts getting positive. And because it's a less than, we can't include that 0. And then we're unioning this up with the next part, which actually starts at the location of the vertical asymptote, which is at 2. And then that goes on to infinity. So the parts where we are less than 0 are from negative infinity to -2, and then 2 to infinity. When we compare this to the less than or equal to, that's where we're allowed to equal 0. So in the equal to part, this at -2, that's equal to 0. So that's where I'm allowed to change that to a bracket. But unlike the polynomial inequalities where all parentheses became brackets, the one at 2 still is a parenthesis because that's not equal to 0. That's an asymptote. So any locations of asymptotes don't switch symbols. They're always going to be parentheses. So a negative infinity to -2 bracket here, a union, and then we have 2 to infinity. So they're very similar. What changes are the locations at the zeros, but not the asymptotes. Are there any questions so far? The less than parts. Okay, so I'm going to erase my highlights. I actually erased my asymptotes too. Oh well. Now let's look at the greater than 0. So where are we above the x-axis? So we're above the x-axis in only one section right here. Everything else is below that x-axis. And so if I was to look at that on the number line as far as the x's, we've got a very small section there between -2 and 2. So we are greater than 0 in that case. We can't include 2 because that's an asymptote. So I'm going to have a parenthesis there. And at -2, it's a 0. If we're greater than 0, then zeros are not included. So that's also going to be a parenthesis. So our intervals where our graph is above the x-axis is from -2 to 2 with neither endpoint included, because we can't actually touch an asymptote and the zeros are not included. When you compare that to the greater than or equal to, the greater than or equal to says any zeros are included. So we have 1 0, and that's at -2. So that turns into a bracket. So this would be a bracket at -2. And then we have 2 to infinity. So the special cases that we have to worry about are what happens at the zeros when we're crossing the x-axis. And then all the asymptotes are always going to have parentheses. Are there any questions here on how that graph translates to our intervals? Okay. So if you watch the polynomial one, you'll see that this was very similar. The difference here is that we're not just worrying about zeros. With the polynomials, we had to worry about zeros, but here we have to also worry about asymptotes as well. And the key is that asymptotes are always going to be parentheses because we can't include those points. And when we do our sign chart, we're going to use dashed lines at the asymptotes like you do on a graph. So I have the steps for rational inequalities. These are near identical to the polynomial inequalities. I'm just going to highlight the differences. When you factor, you need to factor both the top and the bottom. And then you set the factors to 0, both the top and the bottom. So you're looking for where things are on the 0 on the top and the bottom. The top gives you the zeros, the bottom gives you the asymptotes. And we need to know the locations of both of those. The other difference is that with the less than or greater than signs, you use dashed and the numerator solid otherwise, but the denominator zeros are always dashed because those are where the asymptotes are. So the denominator gives you the asymptotes, so those are always going to be dashed. We can't include those. The numerator is actually giving you the zeros or the x-intercepts, which I abbreviate as x-int. And, oh, I forgot that's supposed to say divide because rational expressions are dividing instead of multiplying because we have fractions. So then the other difference is in step 6, you divide instead of multiply, like a polynomial. But everything else, oh, and that should also say divide too. I copy and pasted the directions because they were so similar, but I forgot to change those two words. So everything is basically same steps as with polynomial inequalities. And I actually think they're almost easier because rational expressions are usually easier to factor. The ones that you get are usually easier than what you see with the polynomials. So I actually think that the rational inequalities are much easier than the polynomials. So we're going to just go straight into examples. I didn't make the chart this time and include it like I did before. I'm going to just make it by hand. But you're going to see that the same steps, they're like very, very, very similar. So we have 4x minus 1 over x is greater than or equal to 0. So you have to have one side equal to 0 or greater than or equal, have a 0 on a side. And we've got that. So, and then we need a factor, but we don't have anything to factor here because we don't have any quadratics. There's nothing to factor, we just have linear parts. So if they're already factored, or don't have to do that, your next step is to find the zeros and the asymptotes. And so we do that by setting the top equal to 0 and the denominator, the bottom, equal to 0. And then you solve for x. So one of them is already solved for x. We have x equals 0. So the second one, I add 1 to both sides. I get 4x equals 1. Divide both sides by 4. I get x equals 1/4. So once you determine that, then you do the sign chart. Now at x equals 0, this will be an asymptote because it's the denominator. So we're going to have a dashed line. X equals 1/4 is going to have a solid line because we have a greater than or equal to symbol. So that equal to part means that that point's included. And then I always make sure we're greater than, that part's telling us we're going to be looking for the positive parts. So I'm going to set up my sign chart. So I'm going to write my factors. You write the top factors and the bottom factors. And then I've got two numbers I'm putting on here, 0 and 1/4. If it helps, you can put in where your infinities are to help you remember. And then instead of doing the multiplication underneath, we're going to do division because we're doing the top divided by the bottom. But the rules as far as like the odd numbers of negative signs, your result's negative. Even numbers of negative, your result is positive. That's the same because the rules for signs with multiplying are the same as dividing. Because a negative divided by a negative is a positive, just like a negative times a negative is a positive. So you still just count how many negative signs you have to determine whether you have positive or negative on the bottom. So I am going to put a dashed line at 0 because that's an asymptote. And then a solid line at 1/4. And now I need to pick what numbers I'm going to plug in. So on the left side of 0, let's plug in like -1. That's smaller than 0. Now between 0 and 1/4, this is where it helps to write 1/4 as a decimal. So that's 1/4 is 0.25. So maybe I just want to plug in 0.1. So I need to plug in a decimal between 0 and 1/4. So I'm going to just do 0.1. And then I want to plug in a number greater than 1/4, which is 0.25. And I like whole numbers, so I'm going to plug in 1. There's no reason to have, I could do 0.5, but if I can do a whole number, that's better. And so now I'm going to plug in these numbers in my chart to determine whether the factor is going to come out positive or negative. So if I plug -1 into 4x minus 1, that gives me a -5. So I'm going to write a negative right there. -1, when I have just x, is -1, so that's also negative. And then a negative divided by a negative is a positive, so I'm going to have a positive underneath. Now I definitely need my calculator for this one. I'm plugging in 0.1, so I'm going to have in the 4x minus 1, 4 times 0.1 minus 1. That gives me a -0.6, so that's negative. And then 0.1 for x, and that's positive. Negative divided by a positive is a negative. Now I'm going to plug in 1. So I have 4x minus 1, so 4 times 1 minus 1. That comes out as 3, so that's a positive number. When I plug 1 in for x, that's also positive because that's 1. And a positive divided by a positive is a positive. So now I've filled out my sign chart. And I'm looking for the positive section. So any part where I ended up with a positive for the division, that is going to be where we have our solution. And I'm going to have parentheses at any part that's dashed, and a bracket in any part that is solid. So when I convert this to interval notation, I have a gap here, so I have to have the union symbol. So I read it from left to right. So on the left, I have negative infinity, and infinities always have parentheses. Then I'm shaded until I get to 0, where I'm going to have a parenthesis. Then I have to have my union symbol, and then the next part where I'm starting is at 1/4, and that has a bracket because that can be included. And then we're going on to positive infinity, which has a parenthesis. And that is the solution to my rational inequality. Are there any questions on any of the steps here? Any clarifications, anything? Okay, I'm going to take this as a good sign. No questions. So we'll move on to my next example here. I've got x squared minus 1 over x. Now here I do have to factor because I have a quadratic here. So I'm going to have to factor. And so I'm going to just do that first. We want to factor. So x squared minus 1 is one of our special factors. It's a difference of 2 squares. That factors to x plus 1 times x minus 1, and then I have x in the denominator. So I just need to factor that out. We're not going to do any canceling or anything like that. We just need a factor. Step 2 then is to find the zeros and the asymptotes. So the zeros come from the top and the asymptote comes from the bottom. And you set each of these factors equal to 0. So you're going to have x plus 1 equal to 0, x minus 1 equal to 0, and x equals 0. So since we have three factors, we're going to have 3 equations. And when you solve, you get x equals -1, x equals 1, and then of course our x equals 0. So these first two, those are zeros because those are coming from the top of the fraction. And because we have a less than symbol, this is going to be dashed. The denominator, the x equals 0, this is an asymptote. And asymptotes are always going to be dashed. So basically everything was going to have a dashed line in this situation. And then overall here, we're going to, oops, I was about to write positive. We're left less than 0, so we're looking for negatives. So once you determine all that, that's when you do your sign chart. So I've got three factors I'm going to have in my sign chart: my x plus 1, my x minus 1, and my x. And then I'm going to just write the division thing there. But we're multiplying on the top and dividing on the bottom, but again, it doesn't really matter because multiplication and division, the signs operate the same. So I've got to put in my numbers here. I've got a -1, a 0, and a 1. So all of these have dashed lines. So I'm going to have very badly straight dashed lines. And now we want to pick numbers in each section. So the first section are numbers less than -1. So let's say I want to try -2. Our next section are numbers between -1 and 0. So in this case, we have to pick a decimal. So I usually pick a -0.5. It just seems easy enough to plug in. And then we have a section from 0 to 1. So again, we have to pick a decimal in there. So I'm going to just pick a +0.5. And then we have a fourth section, which is numbers greater than 1. So I can pick like 2. You can pick any number you want to plug in as long as they're in these sections on the number line. But this is generally, I try to pick numbers that make sense and that seem easy. So I'm going to start filling in my chart. I'm going to start with the x plus 1, and I'm going to start from the left to the right. So I'm going to start with plugging -2 in for x. So in the x plus 1, we'd have -2 plus 1, which is a -1. So that's going to be a negative. Then I plug -2 into the x minus 1. So -2 minus 1 is -3. So that's negative. And then we just have x. Well, if x is -2, that's negative. So here we have 3 negative signs. So that's an odd number. So that means our result is going to be negative underneath. Now I'm going to move to my -0.5 and use a calculator for that. I could do it in my head, but I like to double check with decimals. Just I don't trust myself. So a -0.5 into x plus 1, that would be -0.5 plus 1. That gives me a +0.5, so that's a plus. Then I plug a -0.5 into x minus 1. That gives me -1.5. So that's a negative. Then we have x. Well, -0.5 is negative. Here we have 2 negative signs. And that's an even number of negative signs, which means that they cancel out and our result is going to be positive. So I'm going to write a plus underneath. Now I've got my next section with a 0.5. So I'm going to plug in 0.5 for x. So 0.5 plus 1, that's a positive. 0.5 minus 1 is going to give us a negative. Then 0.5 is just positive. I have an odd number of negative signs. One negative sign means my result will be negative. And then now I'm going to plug in 2. So 2 plus 1 is 3. That's positive. 2 minus 1 is 1. That's positive. 2 is positive. And those are all positive, so my result is going to be positive. Are there any questions on that sign chart and how I came up with those signs? Okay, so we have a less than 0, so we want the negative portion. So we're going to have 2 sections here. And so we're going to have a union to put those sections together. And because they all have dashed lines, those are all going to be parentheses. So going from left to right, I start at negative infinity, which has a parenthesis. And then I'm shading until I get to -1, which has a parenthesis. Then I have a gap. Then I'm starting to get a 0, which is a parenthesis. Then I'm going and shading until I hit 1, parenthesis, and then I'm done. So you can see this is a little different from some of the polynomial ones we had, where we don't have two sides with infinity involved. We have a piece with infinity and then a piece without infinity here. And every separate piece, we have to put a union there to kind of combine it. Any questions? Okay. Here's one where we're going to start kind of upping the difficulty a little bit. We have a minus 2 over a squared minus 4 less than or equal to 0. So we're going to start, the top doesn't need to be factored, but the denominator does. So the top stays the same. The bottom, we have a difference of 2 squares. The factors to x minus 2, x plus 2. Now, we're not canceling anything out here. So even though we can cancel out an a minus 2, we're not going to do that because for the purpose of our polynomials, we need to keep that. So that's not going to get canceled out. We're just going to write the factoring. Now we're going to find the zeros and the asymptotes. So I set my top, the x minus 2 equal to 0, and then the factors in the denominator equal to 0. And I solve all of those for a. So we get a equals 2, a equals 2, a equals -2. So the top here is a 0. The bottom here, these are our asymptotes. Or if there's something that can cancel, that could produce a whole, if you recall that from our rational functions here. Because we've got repeated numbers here, I've got an a plus 2. It's both a 0 and an asymptote. The asymptote takes priority. So that means we're going to use a dashed line at that place. We're not going to use a solid. We're going to use a dashed line. Because asymptotes, they're holes, those take priority because we can't divide by 0. And so we just have to make sure that we exclude that. So we're going to have a dashed line at a equals 2. And then we're also going to have a dashed line at a equals -2 because that is another asymptote. So before I draw my sign chart, are there questions on the determining of whether these things were dashed or not and why a equals 2 is dashed?
Hi guys. So I'm interrupting this example to make a correction, which actually I'm recording for the second time because I found out my sound didn't record, in addition to my webcam making everything blurry, so I don't know what's going on. For those of you who attended this live, I did this example and we ended up getting something where the graph didn't match, and I was trying to figure out what was going on, and my initial thought was that there was something about how Desmos was dealing with the graphs. But stepped away for half an hour, came back to it, and all of a sudden, oh, I found my error. So I am inserting the correct steps here, and then we will move on to the regularly scheduled live session where the recording there. So here we have, I have on my screen the slide or whatever that I was doing. And so we left off with the fact that we'd found our zeros and asymptotes, and there is actually a zero that is also an asymptote. And so those end up canceling out when you're looking at the graph, and they form what is called a hole. So when you're looking at graphing these, you want to basically, any hole has to have a dashed line because it's not included in the graph. And actually, there's a alternate way that I recently discovered on how to graph this. But the way that I'm looking at it here, and this does work, so you have to have that point that you canceled out on your sign chart because anything that's excluded has to exist. So we have both -2 and 2 on the sign chart. So it's excluded because it's a hole. And if you're looking at the fact that it has that it's a zero that you're supposed to graph with a solid line because it's less than or equal to, and it's also an asymptote, or this case, generally, if it's not included, that takes priority as far as the number line goes or the sign chart goes. So that's dashed. So holes are dashed just like asymptotes are dashed if it's a, so one way I'm actually going to switch here. So this is what my colleague wrote up for me because I wanted to verify that I was understanding this correctly. And he is looking at it where you cancel those out and then you're doing the sign chart with 1 over x plus 2. But when you make your sign chart, you have to include the hole. So it gets you the same answer either way. But so I'm doing it where I'm including both the a minus 2 that canceled out on the top and the bottom, and then also having the a plus 2 in the denominator. And then I had my sign chart with the hole that was canceled out, x equals -2, or x equals 2, and then with the actual asymptote at x equals 2. And then you plug in values. So I plugged in -3, 0, and 3, and I made my sign chart. And 3 negatives, when you combine, multiply, or divide, those come out with a negative. 2 negatives make a positive, and then all positives, of course, are positive. So our graph, we're looking for less than or equal to 0, so we end up with a negative. And so you're looking for the negative portion, which is from -infinity to -2. And if you graph this, you can see that on the graph. So I think I still have my Desmos open. Where am I at? Okay. So if you graph this on Desmos, you will verify, you will see that the parts where we are less than 0, the part of the graph that's below 0, is from -infinity to -2. Going back to this alternate method, if you choose to do it by 1 over x plus 2 and you have a less than or equal to 0, you can still make a sign chart. You have your -2 coming from the vertical asymptote here. And then you have a hole is also called a removable discontinuity. So we have a hole at 2. And then when you do your sign chart, you can make your sign chart with a 1 on top and then an x plus 2. And then you're looking at the division of these. So we have a dashed line at all vertical asymptotes, a dashed line at all holes or removable discontinuities, and then you fill in your chart. So 1 is always positive, so that's always going to be a positive. And then if I plug in like -3 plus 2 is -1. I can plug in 0, I get a positive. Plug in 3, I get a positive. And when you divide these, you get a negative, positive, positive. So you get the same sign chart. And then we're looking for that negative portion, so it's -infinity to 2. So the sign chart's exactly the same. So you can do the sign chart by canceling out the common factors and then doing the sign chart there. You just have to remember that anything you cancel out, you have to also put on the sign chart. And in this case, when you're looking at it, there's no zeros because it's just 1 on the top. So I wanted to show you this alternate way to do this. There's another way, another explanation I got about graphing it. So this threw me for, so I had made up this problem. This threw me for a loop because I made it up thinking, oh, this will be a great problem. And it came up with this whole thing. Now I've been teaching algebra since 2006. So, why can't I do the math? 14 years. Oh my God, it's been a very long day. It's 8 o'clock right now. I've been going since 8 a.m. So I'm working nonstop. Anyway, so 14 years. This is actually the first time that I ran into this issue where there was a hole in a rational inequality. And and it's like it was like, oh, how do I deal with this? And I thought I knew how to deal with it, and then I actually didn't, made a mistake, came back to it, realized my mistake, and then I also spoke with other math professionals to double check to see if there was something that I wasn't understanding, just to verify that my correction was correct, which it is correct. And I think it's important for you guys to see this, just because one, we're humans, we're not perfect, and two, so that you can see how do you handle when you make a mistake. You can make a mistake in a professional life, and it's good to handle that in a way where you admit your mistake, explain, and I think making corrections is good because it shows you we're human. It shows that we all make mistakes. It's a great learning experience, and I want to make sure that you guys have correct information. And now that I've encountered this, I will be better prepared the next time something like this happens. So this was a special case I hadn't even considered, and came out very interesting. So I wanted to give that correction. This is going to be in the PowerPoint, and now I am going to have the video go to the next example where I had initially started that one out wrong because I forgot that it was a less than 1 and it's actually less than 0. So I started treating it like it was less than 0 and realized, oh shoot, it's not less than 0, it's less than 1. So we'll pick up starting at the correct step, looking at it as less than 1. And hopefully this makes sense to you, and I will talk to you guys later.
There is a 1 here. That is a problem. Because in order to do what we're doing, we have to have one side equal to 0. We're not equal, so we don't have an equation. We have to have 0 on one side. So our first step needs to be subtracting 1 from both sides, because we have to get one side to 0. So that gives us a 3x squared over x squared plus 4, and then a minus 1 less than 0. Now the other thing with these inequalities is that you have to have a single fraction. So I can't have a fraction plus or minus a number. I have to have a single fraction. So we have to basically take this 1 and turn it into a fraction based off of the denominator of the other fraction. So we're going to basically multiply. We're going to write a fraction x squared plus 4 over x squared plus 4. So this gives us a 3x squared and then minus 1 times x squared plus 4. When you combine these, we get an x squared plus 4. We have less than 0. So I have to simplify the left side, and then I start doing the factoring and all that. So this is 3x squared minus x squared, and then a negative 1 times 4, that's minus 4. And then we have x squared plus 4. 3x minus x, so 2x squared minus 4 over x squared plus 4 is less than 0. Okay. So that's our final thing that we're actually going to be doing the polynomial inequality for. And actually, now that we've done this, we can factor the numerator. I can factor a 2 out of there. So I'm going to start the factor step. So when you factor a 2 out of the numerator, you get x squared minus 2. And then we get an x squared plus 4 is less than 0. Okay, so now x squared minus 2 does not factor nicely. I think it will have square roots, so we're going to solve this another way, but we are going to find our zeros and the asymptotes at this point. So I've got x squared minus 2 equal to 0, and then x squared plus 4 equal to 0. So I'm going to add 2 to both sides for the first equation. That gives me x squared equals 2. And when you take the square root, you get x equals plus or minus the square root of 2. Now for the x squared minus 4, you're going to subtract 4 from both sides. So you get an x squared equals a negative 4. And when you take the square root, you're going to get an imaginary number. And you're going to get a plus or minus imaginary because it's negative, and then the square root of 4 is 2. So actually I should write that as 2i. So the plus or minus square root of 2, this is zeros. The plus or minus 2i are asymptotes. But because we can't graph imaginary numbers, this tells us that there are no asymptotes. So there's not actually any asymptotes, so we don't have to worry about that. Now the zeros here, we do have 2 zeros, plus or minus square root of 2. And because we have the less than symbol, we're going to do this dashed. And now I have found that I have run out of space, so I'm going to add in an extra slide. So let me just add in an extra slide, and then I'll start sharing again. Okay, so there's my blank slide. So going back here, we're going to have our zeros of plus or minus square root of 2, and we're going to have dashed lines at those. And the other tricky thing here is when we're going to do our factors, you include the 2 here because that does matter in whether you're going to get a positive or negative, especially if that was a negative 2, that would really have a big effect on your numbers. So if you have a number in front there, you do have to include that on your chart. So we're going to make the chart with 2. We're going to make the chart with our x squared minus 2, and then we're going to make the chart with the x squared plus 4. So calculators are going to be helpful here. So I'm going to have 2 x squared minus 2 x squared plus 4, my number line, and then I'm going to just write results because we've got multiplication and division going on here. And then our zeros are a negative square root of 2 and a positive square root of 2. So before I start making this chart, there may be questions at this point. Are there questions? And if so, what are they? Okay, no questions, then I will continue. Okay, so we've got dashed lines, and that is because this was a less than. Now, square root of 2, or negative square root of 2, I'm going to do this in decimal form so I know what numbers to pick in. That's negative 1.4, so I can plug in negative 2, and that's smaller than that. I'm going to definitely plug in 0, and then I can also plug in 2 on the other side. because that square root of 2 would be a positive 1.4. So I'm going to plug those numbers in to my factors here. Top row is easy because 2 is always positive. So I'm going to just write plus there. It's just positive. So I don't have to think. If I have a number there, you just write the sign of the number, you go straight across. Next, I'm going to do the x squared minus 2. So that's going to be, I'm going to plug in a negative 2, so negative 2 squared minus 2, and that gives me a positive 2. So that's going to be a positive. And then I'm going to plug into the x squared plus 4. When I plug in negative 2, that gives me an 8. That's also positive. So I'm going to have positives right there. Now if I plug 0 in, I get a negative, and I get a positive number out. So here I've got one negative sign, so my result will be negative. And now I'm going to plug in a positive 2. So 2 squared minus 2, it's 4 minus 2, that's 2, that's positive. 2 squared plus 4 is 4 plus 4, that's 8, that's positive. Now I'm also going to have positives. So going back to, we're looking at this, or you can say we're looking at our factored form. This is what we're trying to solve here. So we're looking at less than 0, so we're looking at negatives. So we're looking for where we're negative. So we've got between 0, or negative square root of 2, and square root of 2. So our answer, I have brackets here, it's going to be negative square root of 2. And you don't want to round, you want to leave it in the exact form when you're giving your final answer. And then we've got a positive square root of 2. And that is the result of the rational inequality. That's where the solution is true. Are there any questions? I'm going to graph this one and hope we don't have any weird things going on here. So first, I'm going to actually graph the original so you can kind of eyeball and see what that means. So I'll just use y equals, we have 3x squared divided by, and then it was x squared plus 4. And the original is, where is this less than 1? So I'm also going to graph y equals 1. So the original was asking for, where is our graph below y equals 1? And so you can see that the part underneath the red line, y equals 1, is this curve. And if I look at the dots, it's an approximate negative 1.414, but that is the negative square root of 2. So that's from negative square root of 2 to the square root of 2. You can see our graph is below 1. That's what our original inequality here is saying, is where is this graph below 1? But our rules for solving polynomial inequalities say we have to have it less than 0 or greater than 0. We have to have 0. So we had to instead solve this. So I'm going to solve this one, or graph this one, so you can see. So what we actually had to solve or graph, we've got 2x squared minus 4 divided by x squared plus 4. And in that case, we're asking, where is this less than 0? And you can see it's the same shape. It's just been shifted down 1. And then that way we can use our technique. We still have the negative square root of 2 and positive square root of 2. And our graph is below 0 in between those two parts. So in order to solve, we had to do a little shifting or transformation, but it allows us to get the same answers as far as the x goes. Are there any questions on that? Okay, I have one more. This one's already factored for us though. So I wanted to do something with some things to the fourth, things squared, that sort of stuff. So this is already factored. We've got it less than or equal to 0, so we don't have to worry about that. So we just need to find the zeros and the asymptotes. So that will be our first step. So we've got 3 minus x equals 0. 4x minus 1 to the fourth power equals 0. And then x plus 2 squared equals 0. So I'm going to solve each of these for x. Now the 3 minus x, I'm going to add x to both sides, so that gives me 3 equals x. So since that's on the top, that's a 0. I'll just immediately label that. So this is a 0. And because it's a less than or equal to, we'd use a solid line. The 4x 1 to the fourth power, you basically take the fourth root, and any root of 0 is 0. So you're basically, you can ignore that part and you're solving 4x minus 1 equals 0. So this gives us 4x equals 1 and x equals 1/4. So this is on the numerator, it's on the top, so this is another 0, and because of the equal to part, this is going to be solid. Then we've got x plus 2 squared equals 0. So if you take the square, let's see, so if I plug in -2 plus 2, that's 0, squared is 0, we're still dividing by 0. So we still have an asymptote here. If you square both sides, or square root both sides, square root of 0 is 0. So you're really just solving x plus 2 equal to 0. And so x equals -2. And because this is in the denominator, this is an asymptote. And I was just verifying -2 plus 2 is 0. 0 squared is 0. You're still dividing by 0. So that is going to make it dashed. So I'm going to, see, I'm trying to figure out where I'm going to fit this. I will do my number line on the bottom here. So my three numbers, I've got a -2, I have a 1/4, and I have a 3. And then I'm going to use 3 minus x as a factor. I need to use the fourth version, 4x minus 4 to the fourth power, and then also the x plus 2 squared version. So you have to use the squared version there. Or you can write them, you can write the x plus 2 twice. You can write the 4x minus 4 4 times. It's just easier to use the exponent there. So I've got a solid line at 3. I did not leave myself a lot of, I'm going to move my 3 over so that I can actually give myself some room there. I'm going to actually move my 1/4 so that I have more room there too. Okay. So I've got a solid line, and that doesn't even go through 3. Solid line at 3. I have a solid line at 1/4, and then a dashed line at -2. And so I need to pick numbers in each section. So a number that I can use less than -2 is, say, -3. I have to pick a number between -2 and 1/4, so 0's between there. And then between 1/4 and 3, so I could use 1, and then bigger than 3, so I can use 4. So those are the numbers I'm going to plug in. I'm going to plug them into the factors that I've written. And I'm going to use the exponents and all that. So I'm going to start at the left, and I'm going to do the x plus 2 squared. So it's going to be -3 plus 2, and then you square that result. And that gives me a +1, so I'm going to write a plus. And then I'm going to have 4 times -3 minus 1, and then take that to the 4th power. I got a really big number, but I'm going to get a positive. Then I have 3 minus x, so 3 minus -3 is a positive 6, so that's plus. And all of those give me a plus. Now here's a nice trick. Even exponents always give positive numbers out no matter what you plug in. So I know that these are all going to be positive. And you can test it out. All of those are going to be positive. And same thing with the x to the 4th, because those are even exponents. Because basically you're having, if you have a negative times a negative, it's a positive. Or a negative times a negative times a negative times a negative, you get a positive. Even numbers always come out positive. So I'm going to just fill those in with positive, so I don't even have to check those. And I just need to check in 3 minus x. So 3 minus 0 is 3, so that's positive. Then I have 3 minus 1, which is positive, that's 2. And then I have 3 minus 4, which is -1, and that's a negative. So let's see, I've got 3 positives, positive, positive, and then that's a negative. So now we're going to be looking for where we are less than or equal to 0. So the negative portion. So we're negative in this part right here. That's where we are less than or equal to negative. To 0. It doesn't make sense. So even we have these 3 sections to the left, they're all positive, but you know, we just have one section here. So our answer is just that one section. I'm going to put it up here. We've got a bracket at 3, and then we're going to infinity. And that's where everything is below 0. So I'm going to pull up Desmos again just to graph this one. So on the top, 3 minus x, 4x minus 1 to the 4th, and then denominator, x plus 2 squared. So the question is, where is it less than 0? I'm going to modify my x-axis so you can get a better picture. Actually, let's do -5. Okay, so our graph is getting negative from 3 to positive infinity. You can see that right here. That matches our answer here. That's where the graph is going negative. So that matches what we have. But I want to point out something interesting here. So what if instead of a less than or equal to 0, it had said it was a greater than or equal to 0? So what if this was greater than or equal to 0? In that case, you'd be looking for all the plus signs, but between 2 of the plus signs, there's a dashed line at -2 because we can't have -2. So if you were looking for the positive version, if it's greater than or equal to 0, you would have -infinity to -2 with a parenthesis, union, because you can't have a value at -2 because of the dashed line, so you have to skip -2. Then you would have -2, and it would actually go all the way to 3. You can skip the 1/4 part because of the equal to 0, because it's solid and that's included. So this is an interesting thing where you have to think, well, where am I including values? If it's included, I can just skip it if I'm like highlighting the whole thing. So I'm going to look at that graph again. I can get that. If we were looking for where it's positive, you can see it's a positive everywhere here. except at -2, find -2 on the graph, and this is where Desmos is, I'm going to have to zoom out, -2. Okay, let's center -3 to -1, so I can, where is -2? Zooming out, let's see, if I close, -11, okay. -5, -3. Okay, let's see. We've got some interesting things going on here in this graph. Okay, so -2, that's -3. Sometimes graphing is not the best way to solve these. So it looks like I'm going to have to go up forever to figure out where my -2 is. I'm getting closer. I can tell I'm getting closer. Let's see, that's -9.1. Where is the top of this? There should be a hump somewhere. Oops. And wherever -2 is here, this is really ridiculous. If I change that to 6. Nope, it's still 9, 12. They're really giant numbers. I did not realize how big these were going to go. Okay, well, this is gonna, I can't show you, this is gonna be just ridiculous, but what I was trying to make the point is if you're looking for the parts where it was positive, I was going to show you where it's undefined when you click on the point on Desmos like I did on the other ones, but we're not gonna find that. It is just, it is too high here. So this is one where you would have to trust your sign chart versus using the graph, because the numbers are just so darn big that it would be near impossible to use the graph to figure out where these things are and to even notice that there is a value that's not allowed in there, that -2, and that there's like an asymptote and stuff there. Any questions? This is my last example, by the way. I know you guys have stayed with me for over an hour and I appreciate it. We had some interesting problems here. Good news for you is that most of the homework problems are going to look more like these. So they won't be as complicated as some of these other ones that I have done. But I do like to throw in some complications. These were quite a doozy for these last two that I did. So I do like to do complications. I think I made them a little bit too complicated, but hopefully at least you have the general idea. And you should see much easier ones to deal with than this. So thank you guys for joining.